In the previous modules, we had been looking at the principal component analysis. The module before this, we had looked at some of the very important results related to principal components, primarily how to find them and what are their relationships with the original variables. In today's module, we will be looking at some of the other features, like for instance, what happens when we standardize the variables and then do a principal component, what the geometry of the principal component really means, and what about special structures of the dispersion matrix. What would be the type of principal components we get for this sort of special structures. We will also have a brief look at how to select the optimal number of principal components for our further studies. Now, it is easy to show that this row would have eigenvalues, one of which or the largest of which would be lambda 1 equal to 1 plus m minus 1 into rho. Of course, rho has to be positive for this to be largest, and all the remaining m minus 1 eigenvalues starting from lambda 2 to lambda m would be equal to 1 minus rho. So, you have a multiplicity in this case of m minus 1 eigenvalues equal to 1 minus rho and a single one which is lambda 1 and which is larger than the others. Now, if you calculate the eigenvector corresponding to lambda 1, you would find that p 1 turns out to be 1 by root over p m, 1 by root over m, etc., 1 by root over m. So, the first principal component would come out to be y 1, which is equal to p 1 prime z is 1 by root over m summation I equal to 1 to m z I. And in this case, you can see that the first principal component is primarily the sum of the variables, original standardized variables, divided by square root of m. Would it be the same as doing the principal component on the original variables? The answer is that they would be similar, but not exactly the same, because the eigenvalues and eigenvectors in this case would come out to be slightly different. This is primarily because once you work with the original variables have certain ordering in the sense of they have different weightage. A variable may be large, another variable may be small, etc. But once you standardize them, these advantages or disadvantages are neutralized and they have a different type of impact overall. So, that is why the results would be somewhat different in this case. Without going into the details, because the results would be similar to what we did for the original x's, let us very quickly look through the changes. Matrix notation, we can write the new variables z, these are the standardized variable, as sigma half inverse x minus mu. Remember that sigma is positive definite, so we can always have sigma half into sigma half equal to sigma. So, you take sigma half inverse x minus mu and that gives us the new variable z, and it is easy to see that the expectation of this z would be equal to 0. The dispersion of z would be sigma half inverse sigma half inverse, and in matrix notation you can write z as equal to v half to the power of minus 1 x minus mu, where v is a diagonal matrix with variances on the diagonal. So, if you use this, it is easy to see that expectation of z is equal to 0. Dispersion matrix of z is v half to the power of minus 1 sigma v half to the power of minus 1, and this you can readily see is the correlation matrix. So, now we are using the correlation matrix instead of the dispersion matrix to derive the eigenvalues and the eigenvectors, and that is the reason why there would be a difference. Now, using the same principles, and I will just be stating this result because the proof would be exactly similar. The ith principal component for the standardized variables would be given by yi, which is pi prime z or pi prime v half to the power of minus 1 x minus mu, and the summation of the variabilities of this yi's again would be equal to the summation of the variabilities of the zi's, and in this case remember that rho is a correlation matrix, therefore its diagonals are all 1. So, summation of the variance would be the sum of these diagonals, which is equal to p, or in this case it is equal to m. So, we have the sum of the variance equal to m, and also the correlation between the ith variable, the standardized variable, and the jth principal component would be given by p j I square root of lambda j. That is exactly what we got before, except that we are dividing this by the sigma i's, but in this case it is standardized. Okay? And in this case, of course, the lambdas and the pj's are basically the eigenvalue eigenvector pairs. Kth principal component would now be lambda k by p simply, because the denominator is now p. So, the methods is the same, but mind you, as I said, that getting the eigenvalues of rho is different from getting it from sigma. So, there would be some changes in the result. To do that, it is easier if we look through the usual multivariate normal distribution. So, suppose X follows the multivariate normal distribution m dimensional with mean mu and variance sigma. Now, it is known from the multivariate normal results that the density of X is constant on the ellipsoid x minus mu prime sigma inverse x minus mu equal to c square. So, given a particular c square, the density would be constant over this. Okay? This is the ellipse which has an axis plus minus c root over lambda I e I, where I runs from 1 to m. So, these are the eigenvalue eigenvector pairs again. So, a point lying on the ith axis of the ellipsoid will have coordinates which would be proportional to the pi's in the coordinate system that has origin mu and axis parallel to the original axis x1, x2, xp. Now, suppose we assume mu to be equal to 0 for simplicity only. Okay? In that case, we can break up this c square equal to x prime sigma inverse x as 1 by lambda 1 p1 prime x square plus 1 by lambda 2 p2 prime x square, etc., up to 1 by lambda m pm prime x whole thing square. This is easy to do because sigma inverse, mind you, can be broken up in a spectral decomposition as summation of 1 by lambda j pj prime, and then you pre and post multiply this by x and you get this result. So, what we have now here is that c square is equal to 1 by lambda 1 the first principal component squared plus 1 by lambda 2 the second principal component squared, etc. And this equation defines an ellipsoid in a coordinate system with x's as the axis and the directions p1, p2, pm respectively. Now, lambda 1 being the largest of the eigenvalues, the major axis would lie in the direction of p1, and similarly for the second one, which is lambda 2, would be in the direction of p2, etc. So, what it does basically is it makes a transformation. Remember that we are doing a principal component, it means really that we are making an orthogonal transformation. So, the transformation is done in such a way that first principal component would lie along the more dense part of it. So, it will change direction according to the lay of the distribution form. If you have a distribution with variables which are highly positively correlated, in that case it will use the correlation and determine the direction that way. So, it gives us a very good idea what the principal component really means and how we can get the major axis of the principal component. Next, let us look at some special covariance structures. The simplest covariance structure that we can think of is dispersion matrix is diagonal, that is its sigma 1 1, sigma 2 2, sigma p mm on the diagonal and 0 elsewhere. If we have such a sigma, then what would be our principal components? Now, notice that vector E I, which is the unit vector, E I basically is a vector with zeros everywhere except in the ith position, which has a 1. So, if we use this, then we have the relationship that sigma ei is equal to small sigma ii ei, because this from the matrix sigma ei would be pick up the ith element, which is sigma ii, and we can write it as ei, which is 0 0 1 0 0 into the scalar sigma ii. Now, if we can write it this way, it at once tells us that sigma ii is an eigenvalue of sigma, and the ei's are the eigenvectors, corresponding eigenvectors. So, in this case, the eigenvector, ith eigenvector eigenvalue pair is sigma ii ei. Now, what would be your yi? Yi would be ei prime x, which would simply pick out xi. So, yi is equal to xi, which means that the ith principal component is the ith variable itself. So, what does this tell us? This tells us that nothing is gained by extracting principal components in this case, because the principal components will be the original variables themselves. So, mind you, in this case the variables are uncorrelated among themselves. So, if there is no correlation among the variables, there is no common factor among them, and hence the variables themselves would turn out to be their principal components. So, we do not really do a principal component analysis when the variables are uncorrelated to each other. Let us look at another structure. This is a very standard structure. Let sigma be equal to sigma square, rho sigma square, etc., up to rho sigma square, etc. So, if we take out sigma square from this sigma, then we are left with the correlation matrix. Now, we will work with this correlation matrix. Remember, when you have such a situation, we have a situation like this when the correlation between the different variables are the same and the variances are constant, which is equal to sigma square. So, if you have constant variances and same correlation every pair of variables, then we can have a matrix of this type. Now, it is easy to show that this row would have eigenvalues, one of which, or the largest of which, would be lambda 1 equal to 1 plus m minus 1 into rho. Of course, rho has to be positive for this to be largest, and all the remaining m minus 1 eigenvalues starting from lambda 2 to lambda m would be equal to 1 minus rho. So, you have a multiplicity in this case of m minus 1 eigenvalues equal to 1 minus rho, and a single one, which is lambda 1, and which is larger than the others. Now, if you calculate the eigenvector corresponding to lambda 1, you would find that p1 turns out to be 1 by root over p m, 1 by root over m, etc., 1 by root over m. So, the first principal component would come out to be y1, which is equal to p1 prime z is 1 by root over m summation I equal to 1 to m zi, and in this case you can see that the first principal component is primarily the sum of the variables, original standardized variables, divided by square root of m. The remaining eigenvectors can be obtained orthogonal to this. Mind you, the remaining would have m minus 1 linearly independent vectors, and you can always orthogonalize this. There are several choices for the remaining eigenvectors, and one of the very standard ones is taking p2 to be 1 by root over 1 into 2 minus 1 by root over 1 into 2, and the remaining 0, p3 equal to 1 by root over 2 into 3, 1 by root over 2 into 3 minus 2 by root over 2 into 3, and the remaining 0, and so on and so forth. So, each of these are now orthogonal to each other, but there are several other choices of this as well. More importantly, let us look at how much of the proportion of the total variability that the first principal component accounts for. Now, remember that this would be given by lambda 1 by m, and we have 1 plus m minus 1 into rho by m, and that is equal to rho plus 1 minus rho by m. So, that is the total population variation explained by the first principal component, and you can see that this is going to be equal to, almost equal to rho if either rho is very close to 1, which means the second term is almost 0, or if m is very large. So, if you have very high correlation among the different variables, then the first principal component would account for a very large proportion of the variability, and you need not be looking at the other principal components. So, the next question would be, how many principal components do you think you should be taking into your model? We had been doing this arbitrarily till now. We had been looking at this lambda 1 plus lambda 2 plus lambda j divided by the total variance and deciding on this. But how to be a little bit more objective? How do you choose this? Now, what we can do is, we can have what is referred to as a scree plot. Now, what is a scree plot? A scree plot plots the eigenvalues against the corresponding I. So, you plot lambda I hat against I. Remember, lambda 1 hat is the largest, so you have the first point having the largest value, and then this would be decreasing. Okay? So, you can have join them by lines, and you can see that this would be a decreasing function. And once it's not going to decrease in a straight line, it will be sort of exponentially decreasing. And once you find that there is a turning point, which we generally refer to as an elbow. So, you have your arm stretched out and you break it at the elbow. So, there would be a sort of hinge at the elbow. So, if you have this hinge at this curve, it really means that before this point the eigenvalues are dropping very rapidly, and beyond this point it has straightened out or flattened out sort of, and hence it was not falling very rapidly. So, you do not gain by going from the one eigenvalue to a next one if you are beyond this elbow. So, what is generally done is that you decide on where the elbow is. You can visually see this from the scree plot, and you take the number of eigenvalues equal to whatever the I value is at the elbow point. This way, you would be discarding very little of the remaining informations contained by the remaining eigenvalues, which would be turning out to be very small. So, additional eigenvalues now, if you bring them in, would not account for much variability. And even if you have not a very high percentage of variability by the previous ones, you need to bring in a lot more of the eigenvalues or the variables, principal components in this case, and to explain the variability, which would not be rational, because we are trying to do the principal component so as to minimize the number of variables that we are looking at. So, a scree plot gives us a very good idea of how many principal components we should retain in our further studies. In today's lecture, we started by looking at how we can obtain principal components from standardized variables. We saw that this does not give us exactly the same results as the original variables, because the standardized variables would neutralize the individual effects of the different variables. So, in this case, the eigenvalues and eigenvectors would be somewhat different, but in most cases the results are similar. We also saw how the principal components lie geometrically, in the sense that they would be in the direction of the concentration ellipsoid, the maximum values that this concentration ellipsoid takes in a certain direction. And we also saw the special structures of the variances, which lead to very special type of principal components. Important thing about to remember is this, that if the variables are uncorrelated, then you need not do a principal component, because it does not lead you to any result at all. In fact, you get back the same variables. So, remember, you only do a principal component if the variables are correlated among themselves.